And hello and welcome to Activity 19. And where do we begin when we start a new activity? None other than the first lesson. So we are on lesson 19-1, and we're going to learn about something called the right triangle altitude theorem. So before we go any further, let's always annotate our learning targets. So the first skill word I see in the first learning target is to identify. We're going to identify relationships that exist when an altitude is drawn to the hypotenuse of a right triangle. So first thing we probably need to learn is what an altitude is. Make sure we remember what a hypotenuse is. And most importantly, know what a right triangle is. But once we identify those relationships, we will prove the right triangle altitude theorem. So, if you would, start by chunking items 1 through 3. So we'll draw a line right above 4. And as always, try to complete these items on your own before playing through the video. So hopefully you took a second to try to complete items 1 through 3. I added quite a bit of notes to this just to make sure that we were covering any prior information that we possibly needed. So we've investigated properties and relationships of sides and angles in similar triangles. And so I wanted to recall what the properties of similar triangles were. Similar triangles have corresponding angles congruent and corresponding sides proportional. And so we are given this figure with a right triangle, just to make sure we know what a right triangle is. It's a triangle with one 90-degree angle. And they tell us that line segment AN is perpendicular to line segment ME. So we started with triangle MAE being a right triangle. Then we drew line segment AN so that it was perpendicular to line segment ME, thus creating two more right angles. They also tell us that measured angle M is 70 degrees. So they ask us to determine these angle measures, and I highly utilize this information here that three angles of a triangle sum to equal 180 degrees. But before we tackle this, make sure you can actually identify that there are actually three triangles now. The original we started with, triangle MAE, the original right triangle. Now we have this really small right triangle, triangle MAN, and what we're going to call the medium right triangle, triangle ANE. So just keep that in mind. So there's technically three triangles here. So the measure of angle MAN is 20 degrees. Reason I found that is they told us angle M was 70, and these three angles right here in this small triangle have to sum to equal 180. And here's an even easier hint. If we already have a right angle in our right triangle, these other two angles have to add to equal 90 degrees, right? 180, subtract the 90-degree angle, we have 90 degrees left. So these two other angles are actually complementary to each other. If you remember, complementary means they sum to equal 90 degrees. So I just kind of did that math really quickly, because if this is 70, I need to add 20 degrees to it to get 90. And then I'll use that same concept here for the measure of angle EAN and found 70 degrees because I know that angle E has to be 20 degrees. So then number 2 says justify that the two triangles are similar. Well, we actually learned two similarity criterion, side angle side and angle angle. And if you can't tell from the information you figured out in item 1, we're going to use angle angle to say triangle MAN, this small triangle, is similar to triangle AEN, this medium triangle, as we're going to call it. And again, by the angle angle similarity. So I said the measure of angle M in this small triangle is equal to the measure of angle EAN in this medium triangle. And measure of angle MAN is equal to the measure of angle E in this medium triangle. So they are in fact similar. And the next thing that they tell us is not only are the two smaller triangles similar, or the small and medium we'll call them, but the large triangle is also similar to the two smaller. So they ask us to finish out the similarity statement. that triangle MAN is similar to what? Well, this is where it gets a little bit complicated, but angle M is going to correspond to itself from this small triangle to the large as well, because angle M is a measure in the small and the large. So angle M corresponds to angle M. Where it gets a little tricky is that the measure of angle MAN in this small triangle is actually 20 degrees. So A in the small triangle is not going to correspond to A in the larger, because angle A in the larger triangle is actually the 90-degree angle. So that's why I said A corresponds to E, right? MAN, this angle 20 degrees, actually corresponds to angle E in the larger 20 degrees. And last, in triangle MAN, N is the 90-degree angle, and that corresponds to angle A in the larger triangle. So that's why I put that note here. Those 90-degree angles do correspond. So with that said, we actually have three triangles that are all similar to each other. And notice how I'm classifying them. It's not a very technical term, but just so you know which one I'm talking about. The small, the medium, and the large. So in fact, all three of these triangles are similar to each other. And what that means for us is that the triangles have corresponding angles congruent. That's what we said here. But we're going to utilize the fact that their sides are proportional, which leads us to our next two problems. I'm going to explain what item 4 is. It says name the type of special segment AN is in relation to triangle MAE. This is known as an altitude. And so what is an altitude of a triangle? Well, an altitude of a triangle is a segment from a vertex of a triangle, perpendicular to the opposite side of the triangle. So recall that a vertex is simply where two lines meet. So we had triangle MAE, this right triangle, and from vertex A, you got to almost ignore AN at this point, but from vertex A, we drew a segment from A perpendicular to line segment ME, and that's known as an altitude. Well, now we're going to apply, and think about why we even added an altitude. This altitude is creating three similar triangles, and we know that similar triangles have sides that are proportional. And so the altitude exists so that we can compare corresponding sides of three triangles here and complete item 5. So if you would, draw a line below item 5. Take a second before playing through the video. Okay, hopefully you took a second to attempt item 5. We were given two lengths, AM being 9 inches and NE being 12 inches. And we were tasked to use the Pythagorean theorem and the properties of similar triangles to determine these segment lengths. So the first segment that we were looking for, AE, I actually utilized the Pythagorean theorem for it. And the Pythagorean theorem over here is a squared plus b squared equals c squared, where a and b are your length of your legs. And remember, on a right triangle, your legs are the two sides that actually make the right angle. So those would be your legs. And the third side, c, is the length of your hypotenuse. Now let me explain why I actually used the Pythagorean theorem here and not necessarily properties of similar triangles. Well, we have AN and NE. So if we go up to our diagram, AN and NE are two sides of our medium triangle. So AN and NE are two sides of our medium triangle. More specifically, they're the two legs of our medium triangle. So I believe I said AN was A. I used A to represent the length of AN. And NE was B. So I used B to represent the length of NE. And then I found C, which would be the length of AE. So using a little Pythagorean theorem, the length of AN was 9. The length of NE was 12. So we do exponents first. So 9 squared, 81. 12 squared, 144. Then we combine these two terms to get c squared equals 225. And again, we're not solving for c squared or even AE squared. We're finding c. So to undo a square, we take what's called the square root. Nice thing about 225, it's a perfect square of 15. So c equals 15, thus AE equals 15 inches. So now that I know AE, the length of, and here's the tricky part, AE. There's two ways to view AE. AE is the hypotenuse of triangle ANE. It's the hypotenuse of triangle ANE. That's what we just did. We used the letter C to represent the hypotenuse AE. But AE is also the longer leg of triangle MAE. I'll say that again. AE is also the longer leg of triangle MAE. And that would mean that MA is the short leg and ME is the hypotenuse of the original triangle MAE. So what I'm implying to you is a lot of these segments are actually acting as two different type of segments. Like I said, AE is acting as the hypotenuse for the medium triangle, but it's also acting as the longer leg of the largest triangle MAE. So with that in mind, let's continue on. So now they want us to find MA. And so I use proportions here, knowing that all three of these triangles are similar. I use proportions to find MA and MN. So anytime I'm writing proportion, solving for a certain side, that's the very first thing I'm going to put in my very first ratio. If I'm looking for MA, my first ratio, I'm going to write MA. And so ask yourself, MA corresponds to what? Well, again, MA is acting as the hypotenuse of the smallest triangle, or it's also acting as the short leg of the largest triangle. But we just found the length of AE, 15 inches. So I'm going to say that MA, the hypotenuse of the smallest triangle, corresponds to AE, the hypotenuse of the medium triangle. So we talk about this idea of corresponding parts, and the hypotenuse of these two similar triangles, the hypotenuse, do in fact correspond. So I compared MA to AE. Well, when writing the second ratio, if I started with the smallest triangle, a side in the smallest triangle, and then went to the medium, I have to do the exact same thing. I have to go to a length in the smallest triangle and compare it to a length in the medium triangle. So I used AN, which is technically the longer leg of the smallest triangle, and I compared it to the longer leg in the medium triangle, which would be NE. Filled in the values that I needed. Of course, we were missing MA, so I used X in its place. Cross multiplication. 9 times 15 is 135. X times 12 is 12x. Divide both sides by 12, and we find that the length of MA is 11.25 inches. Now, the last one, MN, where it gets really intense, if you notice the proportion I wrote, is I actually used AN twice. And again, that's because a lot of these segments are acting as two different types of segments in these three different triangles. So the first proportion, again, when writing a proportion and I'm solving for MN, the very first ratio, I'm going to write MN and compare it to a corresponding part in another triangle. So my goal was to find the length of MN, which is the short side. Now, MN can't really act as any other part other than combining it with NE, but MN is the short side of this smallest triangle. So I'm going to compare it to another short side of another triangle. In fact, we know the length, every measurement of the medium triangle, so I'm really using that one here. So MN corresponds to AN. Now, there's another way to view AN. AN is also the longer leg of the smaller triangle, so that also works out. But I'm viewing MN as the short leg of the small triangle and AN as the short leg of the medium triangle. So I'm going to write a ratio using those two. Well, now I'm going to reuse AN in the second ratio as the long leg of the smallest triangle and compare it to the long leg of the medium triangle, which of course would be NE, like we said in the last proportion. So I'm going to replace all of these segments with the known values. MN we'll replace with X because we don't know it. You can use any variable there. We just typically use X. Cross multiply. 9 times 9 is 81. X times 12 is 12X. Divide both sides by 12. And the length of MN is 6.75 inches. Now, with all this math, what we are applying is known as the right triangle altitude theorem. Now, typically with our theorems, we do take a moment to prove them, and on the next page, there is a proof of the theorem. So that's what we're applying here. We're looking at relationships within a right triangle because this segment, known as the altitude, is drawn. And some very special relationships occur because this altitude is drawn inside this right triangle. In fact, drawing that altitude, we created 3 similar triangles and used properties of similar triangles to find missing measures in this diagram. Now let's turn to the next page and actually see what the right triangle altitude theorem states. It says if an altitude is drawn to the hypotenuse of a right triangle, and in fact it was, just like we see here, YE would actually be YE would be the hypotenuse of triangle YEA. And so if an altitude is drawn to the hypotenuse of a right triangle, then the 2 triangles formed are similar to the original. So again, we call this the small triangle, AES, and the medium triangle, YAS. They are, in fact, similar to the original right triangle, YAE. Now, I do want to impress right here that not all right triangles are similar. I think that's something very important to say here, and especially as we move into activity 20 and 21, we'll see that just because right triangles all have right angles doesn't mean they're necessarily all similar to each other. Remember, one of the ways we can show that triangles are similar is if they have 2 pairs of angles congruent. So yes, they will have at least one pair of the right angle congruent, but there's got to be a second angle that's congruent as well to say that those right triangles are in fact similar. Now, this is a proof of the right triangle altitude theorem. We're not going to work through it, although this is what I want to stress. The right triangle altitude theorem, if an altitude is drawn from the vertex to the hypotenuse of a triangle, a right triangle, then the 3 triangles that are created, or the 2 that are created, are similar to the original. And so this statement is actually true. Like I said, we're not going to work through this proof, but we typically work through it just so we're able to say that the theorem is valid and we can start using it. But we did just use it on the previous page. So if you would now turn your attention, to item 7, the last thing we're going to do today. You can go and draw a line if you will. And complete item 7 before playing through the video. Okay, so I absolutely love this exercise here, and I think it's going to really pay off to several of you, especially on that first page of this lesson, that we're trying to understand how these segments related to each other, how to figure out which segments were corresponding. So one of the easiest ways to tell how these 3 triangles, remember again, if an altitude is drawn to the hypotenuse of a right triangle, there are 3 similar triangles. To determine how these segments correspond, we write them or draw them in the same orientation. That's why they said draw with the right angle in the lower left position. Because these 3 triangles are similar, we can view it as this small triangle dilating to create this one, and then this one dilating to create this one. So it's just an easier way to view these 3 similar triangles and which segments will correspond. For example, angle D of the smallest triangle actually corresponds to angle C of the largest triangle, because angle D in the smallest triangle is the right angle, and angle C in the largest triangle, or technically angle BCA, that's the right angle in the original triangle. So we're able to see how segments correspond and write proportions, right? The short leg of this smallest triangle is going to correspond to the short leg of the largest triangle. So in fact, DA, this segment right here, corresponds to CA. Well, interestingly enough, CA is also the hypotenuse of the smallest triangle. So this is a great benefit, and I encourage students that are working on the Lesson 19.1 practice, I encourage you to try this first, separating item 8 into 3 similar triangles with the right angle in the lower left position before attempting to find the different measures that you need. So that is the end of Lesson 19-1. As always, go back and reevaluate your learning targets and complete the lesson practice. Thank y'all for watching.